Good evening. Hello. So I am going to be streaming some more hardware stuff today. I'm going to drop this music volume down a little because that's quite loud. Slightly distracting. There we go. So yes, more work on the the lighting stuff. So I put together a diagram to make it sort of slightly clearer as to what the plan is. And I apologise that I look kind of rough. I woke up late and then didn't get much. Well, I say woke up late. I woke up about an hour ago, so. Standard indeed. Yeah. So I put together a diagram. So effectively, what we got here is oh, it'll just help if I actually show you the diagram, doesn't it? There we go. Not just my ugly mug. So we've got this cabinet. This sits at the legs. Well, one of the legs of the gazebo. So we've got 230 volts coming in. And then obviously into this 24 volt power supply. I think this is 20 amps at 24 volts. In fact, yes, it is. I went and found the thing last night. So it's 20 amps, 24 volts. This then goes to a 24 volt to 5 volt buck converter, just for converting, for voltage for driving the rest of the circuitry. This is actually slightly wrong. Technically, what happens is this 5 volt buck drives the ESP32 dev board, and then the other two boards are driven off of 3.3 volts off the internal regulator. I might switch this around slightly because I'm worried about the driver power on the RS485 side. Because it's technically possible that the RS485 drivers can pull a fair bit of current, just because they're needing to drive those lines. It's a surprising amount. So the 3.3 volt converter on the, I think it might even just be like an LDO on the ESP32 board. It might not have enough juice for that. It might just melt. So which is obviously not good. I might switch this around and actually have both a 5 volt and a 3.3 volt converter here. Drive the ESP32 board off the 5 volt input. There's some benefits to doing it that way. And then drive the other two directly off at 3.3. Although the INA219 can definitely run off the ESP32. No problem. Hello, Pyro, and hello, Dan, and hello, anybody else who's in the stream. I can't actually see who that is at the moment. That's a good point. I should probably bring up my proper mod view. There we go. See what I'm doing. So yeah, so then we got this 24 volt line that comes out to each of the nodes. Gets dropped down to 5 volt by the buck converters, which then also drive the RS485 nodes. But also the 5 volt drives the LED strips. So this is actually a very high current converter. I think it's like 30 amps or something. Might even be a little more than that. I can't actually remember how many LEDs. So I started this project when? Like more than 2 years ago, I think now. It's been a long time. And it sort of sat on the back shelf for a while because various reasons. ADHD doesn't help. But I think I calculated the other day, I think there's 288 LEDs per strip, and they're RGBW, not just RGB, so the current consumption is fairly chunky. Well, yeah, on top of this sort of topological sort of diagram, I put together a cabinet because I wanted to make sure that the cabinet that I was looking at... Oh, I just realised I didn't do this. There we go. The cabinet I was looking at, I wanted to make sure that it would all fit. why I landed on RS485 over Ethernet. So RS485 is differential signaling, and the easiest thing to do. Ethernet receivers on the other end would have been complicated and expensive, and would have needed firmware on each device, probably to then, well, definitely to then convert things back over, and I didn't want to mess around with that. I know that you can do WS2812 like protocols over DMX, DMX or RS485. They're effectively the same thing. It's just DMX requires a firmware on the node side, because DMX is literally just RS485, but it's got a framing packet in there for telling you what channel you're setting and blah blah blah. But you can actually drive these. These are actually SK6812 RGBW LEDs. So you can drive these directly out of an RS485 receiver, because the way that RS485 works is it's effectively just a differential signaling to single-ended signaling converter, or vice versa. There's no like weird automatic framing of data or anything like that actually goes into the drivers. So it's effectively a convenient way of doing differential signaling over to here, and then converting it back into just single-ended for the receivers. And I want differential because it's outside, so I want immunity to common mode noise. So if you've got a bunch of RF noise in the environment, it'll couple onto, because they're twisted pairs. These RS485 signals are going over 4 pairs of a Cat5e cable. I also changed a bit of what I was doing. I'm going off on a tangent here, but I'm changing a bit of what I was doing because Robert Ferenek on YouTube happened to drop a video with Rick Hartley, who, if you follow me on Twitter, you'll know I'm a big Rick Hartley stan, because the dude is a genius and has a ridiculous amount of experience in electrical engineering, but does a lot of talks on things like EMI. But they happened to do a video on. I actually forgotten now what the actual topic of the video was supposed to be, but towards the end of the video, Rick was just going through some slides super quick, and Robert happened to spot one with an Ethernet connector, and it ended up on this like side conversation about Ethernet, shielding issues, grounding of differential signals, like grounding of Ethernet across multiple nodes, and it turned out to be exactly some of the stuff that I was like sitting and being concerned about in terms of this design. So I've made a few changes and now massively better understand the way that all of this sort of comes together in terms of that issue. But anyway, what was I saying? See, I just keep going on tangents here. It's effectively just RS485 because it's differential and it's outside. So yeah, the cabinet. So this is Draw.io measures everything in points. So this is 1 millimeter per point. So this is actually to scale, which is how I realized that I wasn't going to have enough space to get all of the stuff that I wanted to get in the way that the cabinet. So the cabinet, this is the thing that sits on the leg of the gazebo. It's going to be mounted to the leg of it, and this is the controller, basically. So I already have this 24-volt, 20-amp supply. So all of this is to scale. So there's a DIN rail under here, DIN rail here, but like 200 millimeter horizontal. So this is like the internal diameter is like 200 and something, like 215, I think. And then vertically it's some other number that I can't remember. I know that externally it is... Oh, I can't actually see from here, but anyway. So we got down in the bottom right here. So what I had to do is get 2 smaller DIN rails here. So one, there's a 100 millimeter one here and another 100 millimeter one here. Because this is a cheap cabinet heater. Now, if you are unfamiliar with deploying electronics outside. One issue is that the temperature regularly drops below the dew point. The dew point is for a particular humidity in the air. What temperature do you need to get to where condensation will just like start forming on surfaces? Which means that even if this was completely airtight, there's still moisture in the air on the inside of it, so that would still happen. So what you do is you get these cabinet heaters. They can be quite pricey. I found this one on eBay for like £18 used, and it's a commercial one with an inbuilt thermostat. Well, actually, it's got a clip-on thermostat, but this is the thermostat, the red bit here. And basically, all it does is you plug it into the mains, and it keeps the temperature between, I think it's like 15 degrees C and 25 degrees C. So it goes on at 15, off at 25, and there's a little hysteresis in that. So this will keep the internal of this above the dew point, at least sufficiently. What I might do is stick some silica gel bag in here. I actually have like a really big silica gel bag, like a massive one, but I don't think it'll fit in here. But I might just stick a couple in there, just as like a desiccant, just for just a couple in the bottom, because as long as this cabinet heater's on, it will actually, in fact, if I put them on top of the cabinet heater, silica gel actually drives off moisture when you get it above a certain temperature. I think it's above about, it starts driving off moisture when you heat it above about 35 degrees, like 35, 40 degrees, which the surface of this will reach. And it'll just keep the moisture levels, the humidity levels down low enough, and this will keep it outside the dew point mostly, enough that it'll keep everything nice. So what I got is an isolator switch. So DIN rail, 35mm DIN rail is super useful because you can attach just like standard breakers to it. Pretty sure they fit on 35mm, and it's not the like really weird small one. That's something to double check. But yeah, effectively, there is a DIN rail under this. You just can't see it because it's hidden. But the mains comes in through the left, comes down, goes into the isolator. This is effectively just a switch that if you turn this off, no mains anywhere else, which makes it easier to work on. Then I've got a pair of RCBOs. So in a normal sort of modern breaker box, you tend to have, well, at least in the UK, the US is a little different, but in the UK you tend to have RCDs on the main input, or RCBOs, but usually RCDs. So RCDs are residual current devices. All they do is check whether the current going through the live matches the current going through the neutral, because if it doesn't, well, there's some leakage to ground elsewhere, or leakage out to some other place elsewhere, which means that somebody might be getting shocked. So all it does is basically look for, usually it's 30 milliamps of differential current difference, and if it sees that, it trips. And there's a time curve on that, depending on how much current and before how long it trips. That's called the curve of the breaker. So you get like type C, type B, type A, blah 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 blah. So RCDs, the only thing that they do is they look for that that differential. Then downstream of that, you'll usually in the UK you get like split systems. So you'll get a pair of RCDs, you'll get a main breaker. Then you'll get a pair of RCDs, and then there'll be a bunch of MCBs off that. And MCBs are miniature circuit breakers. All they do is overcurrent. So they just look for high current on the line. If they exceed the current that they're rated for, they trip. Which is why often when you trip something with a ground fault, everything goes off, because the RCD upstream of your MCBs goes off, because the MCBs don't detect the residual current. RCBOs do both. So RCBOs look for overcurrent, so they're residual current breaker with overcurrent. They look for overcurrent, but they also look for that current differential, the residual current that then trips if there's a short to ground, like somebody shocking themselves. The reason that people don't just go with like full RCBO everywhere is that they're expensive. Like getting them on the cheap, I think I got each of those for like about £8 or something, £9. But obviously that adds up if you've got a lot of circuits, and they're double width as well. Generally, you can get single width ones, but I prefer the double width ones because when they break both the live and the neutral, which means that if you've got a swapped phase, it will cut the yeah, exactly. Yeah, £8 is super cheap. If you wanted to buy them new, you're looking £30 to £60 each, and 30s even that's on the cheap. Yeah, you're looking quite a lot. Anyway, so we've got one RCBO just on the 24 volt supply, and another. Yeah, you can see why I was happy when my landlord was like, "Yeah, sure, we'll do a full modernization, and you can have RCBOs on every circuit." That was great. To be fair, it's like £1,000 worth of work, but totally worth it because the RCD. I mean, I'm going on a massive tangent here, but the RCD upstream breaker thing is a nightmare for nuisance tripping for a whole bunch of reasons, but mostly because every house has like really cursed wiring. Like, you can't trust the wiring anywhere in any house, really, but often there's something cursed somewhere that causes, like, real weirdness. Like, you'll measure current across two different neutral lines and you'll get, like, a 30-volt differential, and you're like, what? Like, what's going on here? So you can get all sorts of, like, weird things happening, and we were getting really bad... Yeah, you know what's funny? I was just thinking about that as I was talking about this. So Dan got me an ADHD storytelling quote, which is behind me. I bought a frame for it, but the frame is ever so slightly too small. I need to get it cut down. But yeah, I have an ADHD storytelling poster behind me somewhere, and I need to put it up over there. But it's the one where it's like normal person telling a story. I think there's a picture of it. ADHD storytelling. I'll find it because it's very funny. Is it? Oh, it's by Danny Donovan as well, who is fantastic, but like, yeah, check that out. Oh, sorry, Dan, give me a minute. You got timed out because for some reason I thought you were on the weird. Pretty sure you're in there. Did Nightbot? Oh, Streamlabs did that. Yeah. I forgot. So it was a while since I'd done like been working on. That was weird. Sorry, I just went to go log into Streamlabs and I got a picture of the lead singer of Avenged Sevenfold. A little weird. Wasn't expecting it. Oh, I don't know what's going on here. Streamlabs bot. Sorry, I'm gonna have to look into that later. I think I have like now 3 bots set up, and they've all got conflicting rules for things. But I'll have to look into that. I thought I'd added you to the allowed users list, but apparently that's only on Nightbot, not on whatever the hell the rest of this is. So I need to go and faff about. But yeah, so I'm doing it again. All over the place. Right. So yeah. Yeah, they swapped out all of my basically took out my old consumer unit and switched it over for a full metal construction one with RCBOs and everything, and it's great. We haven't had a single nuisance trip. The nuisance tripping that we were getting was like really bizarre as well. Like we'd get MCBs tripping over RCD faults. And you'd have to flip the MCBs off and then back on again to get the RCD to come back on, which makes no sense whatsoever unless the MCB is shorting, but the MCB can't really short. Like there's no wiring path in there for them to do that. So very weird, I think that basically just all of it was old and faulty, and it was all the cheapest possible products, so yeah, what do you expect? Anywho, yeah, one RCBO, I think both of these are 6 amp RCBOs because I figured out that based on the, I think it's, what is it? It's 24 volts at 20 amps. So 24 over 230 is about 10%. So it's, yeah, I think, yeah, it's about 2 amps on here. Should be, I think it's actually more than that. It's about 1 point. Yeah, that was it. So because these switch modes are power supplies, while they're if you ever look at switch mode power supplies, particularly PC supplies, PC power supplies, the rated efficiency, so you get this, you know, these 80 plus gold, blah blah blah. The rated efficiency is actually only within a specified load range. And if you ever look at the data sheets for these, the specified load ranges only go about as low as 50%. So if you buy a, let's say you buy a 100 amp power supply, right? A switch mode, 100 amp power supply, and you drive it at 10 amps or less, you're probably getting like 50% efficiency, if that. Like, they're really inefficient at lower power, which is one of the reasons that you really shouldn't over spec your power supplies to a ridiculous degree, because you lose a crap load of efficiency. And like, while thermally it doesn't matter quite so much, because, you know, you got this big chunky power supply that's designed to be able to dissipate all of that heat, you're still wasting a lot of power. Like 10 amps at however many volts, let's say it's 10 amps at 24 volts, that's 240 watts. If that's 50% efficient, you're wasting a ton of power. Like, that's a lot of power, and that's a lot of heat to kick out. So you're heating your room up, and yeah, it's crap, basically. ATX power supplies are bad for that, which is one of the reasons that this rig is so damn inefficient, is because I've got two Xeons, and it's a dual socket Xeon 8276L pair of chips in there, a ton of RAM, and 2080 Ti. So like, you need a crap load of current for when you're really hammering it, which means you need like a, you know, however many, you know, 1200, 1400 watt supply. But for day-to-day usage, you're wasting half your power. One of the problems with that, one of the things that's being fixed with that, is the new ATX 12 volt. I think, is it literally just called 12 volt ATX? The new ATX 12 VO. One of the cool things about yeah, quite. And don't forget that that's on top of, you know, my full server rack over there with all of the gear that's in that. So yeah, like I this is one of the reasons that I get so into like monitoring all of the power stuff, which is the other project that I'm working on. That was another thing that they did when they put the new box in. I managed to bribe the electrician with a decent cup of tea, and yeah, and the hot tub and all of my lighting and all that. Yeah, yeah, I managed to bribe the electrician with a decent cup of tea, and he put me in 2 sockets downstairs, because I had the parts for it. 2 sockets in the basement, plus put SCT split current transformer current sensors on all of my circuits inside the box, and routed them out for me. So that's going to be very helpful, because it's all nice and tidy and labelled and everything. So that was very nice of him. Very useful. Anyway, getting back to the task that's at hand. If you can't tell, I only took my ADHD medication like a bit over, well, it's like an hour and a half ago. So I'm slightly coming up, hence my rambling. So yeah, so we've got this these RCBOs driving the good evening. We've got the one driving the cabinet heater, so that's kept separate, and then one of them driving this 24 volt. What I haven't drawn on here, because it was getting messy, is that this 24 volt supply will then go out through here. Now, I did have 2 INA 219s on here. Now, part 1 of what happened here was, so you might be able to tell that it looks kind of weird that all of this is on top of here. So the way this is actually working is, You might also be wondering how I'm mounting this board onto the DIN rail. I found these really cool little, let me find them. I did have a tab open, but if I don't, it'll be in my eBay purchase history. Are they over here instead? There they are. These cool little things. So these, basically these clip onto a DIN rail, and then they got 3 holes in the top of them. Let me flip it over, and you basically just screw into these, and it's 25 millimeters between the outer 2, so it's 12.5 pitch. So yeah, that's useful. And they're only 2 centimeters high. And this box is 14 centimeters deep internally, I believe. It might be slightly less than that internally, actually, but it's more than enough. So basically, these screw into a hardboard, so it's like a dense hardboard backing on the inside of the cabinet. I think I actually have the cabinet up here because I haven't bought it yet. I put it in my basket. Sorry, I've got a lot of tabs open because I've been working on various things. Here it is. So this is the cabinet that I'm getting, which if I search for the other, so yeah, this is the thing, 360 by 252. Internally, it's 327 by 222 horizontally. Sorry, I'll zoom in slightly because I just realised I'm kind of... There's an unfortunate thing about having 4K screen and then having to stream at 1080p is that everything gets sort of crushed down a little bit. But yeah, so this comes with a rail on the back, which makes it easier to mount. If I search for, I didn't want to do that. So basically, this product is just this product with the backing rail on it, and this shows you this is the picture of the inside. So yeah, we've got this hardboard backing on here that you basically screw everything to, and then these 2 little retainer clasps can be unscrewed. The brass retainers can be unscrewed to pull the whole thing out. So the idea is that you can mount everything on this hardboard and then just push it in and then turn it and job done. The only slight concern I have is that I think this bit at the bottom might have like a lip sticking out, which might, depending on how I've got all this set up, catch on the corner over here. So I might need to just remove that and cut it down. But that's a trivial amount of work, really. So the all of the DIN rails will mount on that, and then all of this all clips together. These are here are just connectors. I haven't quite worked out what I'm doing that. Anyway, with because it's deep enough, I can what I'm doing is I'm getting a piece of MDF, and what happens is because this power supply isn't DIN rail mount, it's actually just like a standalone supply. It does have screw holes in the bottom, so what I'm doing is I'm getting a piece of MDF, cutting it to the size of the it's only thin MDF, like I think it's like 4 millimeters, 5 millimeters or something. Cutting it to the size of the board, spraying it down with I've got some fireplace paint. The reason I want to use fireplace paint is one, I've got a bunch of it that I'm not using, but 2 is that I don't like the idea of having a high current power supply next to MDF, because MDF is basically just like brilliant firewood. So if I spray it down with black fireplace paint, it offers a little bit of thermal resistance to stop it from just like catching fire. It just a slight amount. Then what's happening is 4 holes drilled in the bottom, or however many holes are on the underside of, how many screw holes are on the underside of this power supply, and then that will basically screw into the MDF, and then the MDF will then screw into the there'll be so what will happen is the DIN rail mounts will screw into the MDF, and then the MDF will screw into the power supply. Then with the remainder of the MDF, what I'm doing is I'm getting magnetic, it's like flexible magnetic strips with adhesive backing, sticking that to it, and then the rest of the PCBs will mount onto that, and then that will magnetically stick onto the top. And the other thing that's going to happen is on the top of that piece of MDF, there will be a pair of plastic, it has to be plastic, but hard plastic like ABS brackets. And what will happen is they'll slot over the top of this so that because it's only magnetically held on, it can't slide down. And these terminals are covered, but obviously I don't want it sliding down and banging into these RCBOs. And, you know, this is mains and this is not mains, so not great. So yeah, that'll be kept isolated. If I can find a way to do it cheaply, I might. It might just be a case of like just finding some. I never remember what it's called. You know, like the hard clear. Is it acrylic? The stuff you sort of vacuform with. The thin plastic, but it's you'll often find it inside like old oscilloscopes. You'll open them up, the old CRT ones, and you'll find this like big plastic, like flexible plastic sheet that like drops over in between. You find it in servers as well. Gets between the like the mains power supply stuff and the not servers, but like network switches and stuff when you open up any kind of like appliance. Is it styrene? I don't know whether it is styrene. It's more like styrene's like foam, isn't it? Yeah, no, it's not styrene. It's I think it's just like I think it's PVC. It's PVC. Because it's the same stuff you vacuum with. It's just thin PVC, basically. And what I'll do with that is I'll build a little shield thing that goes around this, and then it'll have a little cutout. So it's like a little. You can just fold it over and effectively just sellotape it or Captain tape it or whatever, and it'll just be like a little thing that slots over the RCBOs just to give it a little bit more electrical protection. Just to anything falls on it, you know, nothing shorting out. I mean, the RCBOs are all short anyway, and this is then upstreamed to an external. So where this connects to outside, it goes to an outdoor socket, which then has an upstream isolator, which then goes to a secondary consumer unit, which has two RCDs in there. So it got an RCD on each. It's got an RCD on the outdoor sockets, and then that goes to an upstream breaker, which then goes back to the consumer unit in the basement, which then also has another RCBO, and then the upstream breaker. So it's like multiple breakers all the way around. I'm like not taking any. I'm not messing about with getting myself shocked. Just keep in mind, this is going in this whole system is going on to a gazebo that's going to have a hot tub underneath it. So I mean, the hot tub normally sits out there. We've moved it out of the way for the moment just because of wanting an outside space for lockdown, which then, of course, they ruined by changing the tier that we were on. But obviously, I don't want to be wet and getting 230 volts through me because that's bad. You know, I can take a 230 volt shock if I can go and then, you know, my arm aches a bit. But if I'm wet and standing on the floor outside, that takes the threat level from all that hurt to I'm dead. So yeah, ideally these would be 10 milliamp. These are 30 milliamp shock rating. So they basically they trip on 30 milliamp ground leakage. Ideally these would be 10, like you'd get in a shower. The problem with that is the inrush current on the 24 volt supply would make it quite difficult to make that work without it just tripping. The supply has it's just a cheap supply, and I'm pretty sure the inrush current would just mess that up. They tend to break a little bit on high inrush current. They're usually the 10 milliamp ones are for bathroom stuff, and the devices themselves then tend to be rated for being used in that way. The other thing is that the 10 milliamp breakers are really expensive, and they tend to only be RCDs. You tend to need a separate breaker, and I don't have space. I just don't have space. There's not enough space for me to get it in there. So unfortunately, that's not happening. If I can manage to find a 10 milliamp RCD that once I've put all this together, if I can find a 10 milliamp one, that if I shift this cabinet heater over slightly, I can fit it on this second rail, the second bottom rail, then I will. Because the 10 milliamp rating is designed for wet environments like showers, and obviously a hot tub is that as well. So ideally I'd be using that. For now, 30 milliamps is fine for this generally, and this is all generally safe. So the thing I realized is that because this is 20 amps, what I was going to do is just use some cheap INA219. So if you're not familiar with INA219, they're current sensors, bidirectional current sensors. So they measure, well, they're power sensors. So they're an IC that basically you hook up I actually have a thing for it somewhere. I think we've got the datasheet open. Yeah, here it is. Yeah. In fact, you know what? Might as well use this. So that's not very useful to you, but wait, that's not what I was looking for. Sorry, I thought that was the INA219, but it isn't. Where are we? Sorry. I did have a datasheet open for it. I'm just find it. INA219. There it is. So yeah, here we go. Yeah, so hello, happy little PCBs. So yeah, basically all this does is takes an input voltage and puts it over a shunt resistor, and then measures the current and the voltage at the same time, and then turns that into a power reading. And you can read the current, and there we go. Here's the general schematic I was looking for. So you can read the voltage, the current, and the current power, the apparent power. So what you get is you get a supply feeding a load, and you put it over a shunt resistor. I do need to recalculate my shunt resistors apparently, because I was under the impression that it should be 80 millivolts, not typically under 50. So interesting. I should probably modify that then. But yeah, effectively the resistor in line with the load dissipates power at its I square P equals I squared R. Yes. Yes. So yeah, it dissipates power, which means P equals I squared R. So my brain stopped working and I couldn't remember whether it was I squared R or I squared over R, but then it doesn't make sense for it to be I squared over R. So yeah, it basically drops a voltage over the resistor proportional to the current, which then it sensors and then figures out based on how you configured it. Yeah. I mean, that's just standard Ohm's law. So that is quite useful. The problem is that if you go on eBay and try and find any of these cheap breakouts for these, they're like max current 3.5 amps or something, like not even that, like 2 amps or something, which is useless to me, because I need 20 amps of detection on the 24 volt line. So it turns out that JLC have INA226 in stock. They normally stock the INA219, but they appear to have run out. They've run out. And if anybody's wondering why JLC's stock seems to just be getting worse and worse over time, I found out. They're moving factories. They're moving to a much bigger factory, which is saying something because their current factory is huge. But they're moving to a new factory, so they're not currently restocking any parts until they move, and then they're going to do a complete restock, which will be very nice. they're expecting that to happen. I think it's in a few months. Yeah. Well, so the thing about the thing about the actual current shunt over here is it can be anything, because it's only measuring a differential voltage. There's no current actually flowing into this device, so there's no maximum current rating on this. You just change the shunt resistor. Yeah, exactly. So what I'm going to be using is an INA226, which is effectively identical. Like if I INA226, oh, that's not what I want. Which, as you can see, is identical. It's basically just it's the same thing, but there's the only difference is the 226 has a higher common mode bus voltage, 36 volts, which is good because this has it's like 20, what does it say, 26 volts or something? 26 volts. So while I'm only running a 24 volt supply, 26 volts is a little on the 2 volt. 2 volts is a little. The overhead isn't much, so you don't give yourself much wiggle room. For just running the power supply at various loads, the voltage is likely to swing about a bit. So having a 36 volt common mode voltage limit is a little bit nicer. JLC have it in stock. It's 91 pence a unit with a minimum of 5. The main reason that you can't use the main reason that the breakouts are like that is because the current carrying capacity of the board isn't high enough. Like, you can't run 20 amps down a single 100 mil pitch header pin. You will melt the header. So you would need multiple, which is not very convenient for a mass market product where you're probably only actually trying to measure, a few milliamps or, an amp or something. You're not trying to measure an absolute ton of current. So you need chunkier connectors, basically. And also the shunt resistor needs to be chosen for a particular current range. And the lower your maximum current target, the better... there's a noise floor on the ADC, but generally the better resolution you effectively have. Like, the lowest significant bit of the current reading will represent a smaller amount of current, meaning you get more precise measurements, which is good if you're just trying to measure something that's pulling less than a milliamp most of the time. But in this case, I'm trying to measure something that's pulling many amps. So I will have to, then I was like, right, okay, so I now need to build my own INA226 breakouts, which is another thing, and another thing to get made. And then I thought, well, if they got a 5 minimum anyway, why not just put them on the board? Like, why not just put them on the board I'm designing now? And then I realized they want 2, because I want to be able to measure... one of the things I want to be able to do is sorry, I'm giving you a sneak preview of that, aren't I? Those? Yeah, it's here. There's a multi-channel version. In this particular case, I'd rather just use the INA226 because it's simple, it's a small part, and it's cheap enough, and it's just there, and I already know how to use the INA219, and the INA226 is a drop-in replacement, so it's just kind of convenient, and it's small enough. So what I realized that I want to be able to do, so I know I want to be able to measure the current pull of whatever supply is driving this board. So the problem with the Pomeroni one is the current limit. Like Pomeroni INA260, if I remember correctly. If you look at the they can only do 15 amps continuous, which is more than some of the others, but 15 amps continuous isn't enough. I need closer to, exactly, you need much higher. So what I've done is, which you might be able to see here, is I put 2 of them on every board, because for the total price, which is £9 and 19 pence for the chips. It's not a lot. It's fine. And it means that conveniently, if I want to diagnose a particular board, I can actually just plug into this. Like I can. This is a completely isolated circuit at the bottom. It's basically just tacked on. So you've got this. So these are 7.68, 7.62. What's 300 mil? 7.62. So 7.62 millimeter pitch headers. These are rated for a lot. I pair 12. Why is autoplay not on? There we go. Sorry about that. These can basically, chunky boy headers. These are actually terminal blocks. So they're 7.62 millimeter terminal blocks. Oh, and by the way, how I didn't think about how useless it was going to be to just search 7.62 millimeter on eBay, because of course everything you get is bullets. So there you go, 300 mil bullets. That's what I'm going to call them from now on. 0.3 of an inch. So these are big chunky headers that are rated for a lot of current. I think they're something like I did look them up, but it was a lot. There we go. Here's one of them. Where are we? How many amps? Oh, I can't find it now. But yeah, it was a lot. It was like 30 plus amps, if I remember correctly. So what this is really is here. This is all I've added in. And I need to change these current resistors because I didn't realize that the circuit, the datasheet recommends actually 50 millivolts differential over these. Not 80. I think 80 is the maximum, so I think it recommends the 50 because that's the best measurement range and also gives you some overshoot. So what all this is basically is an I2C bus with pull-up resistors, a pair of INA 226s, a TVS diode, which is the same part as I already have up here for the data lines anyway. And then a pair of terminals. So on the actual real on the driver side, that's not what I wanted. On the driver side, I've lost my where was my that's here, yeah. So on this driver side, I'm only using the drivers. Obviously the receivers are all disabled. And I'll get to that. I'll get something I did with that in a minute. But yeah, disabled the receivers. So it's just the drivers. And then what I can do is the headers will be, I think, on this side facing downwards. I think that's correct. Actually, I think it's on this side facing downwards. But either way, I can move them about. And what will happen then is I can run the 20 amp. So I can run the power through this connector and then back out to wherever. So this 24 volts, and that's the other thing is that the it will go into here and then it will go back out. So this 24 volts is what goes out and drives all of these nodes. So instead of having these INA 219 breakouts, it will actually go onto this node. It will go into here, and then on the actual nodes themselves, the chips and all of the resistors and whatever will all be populated, but the connectors won't be populated. So they'll just be there doing nothing. They won't be. There's no. There'll be supply going to the INA 226 chips, but there'll be no no data on the I2C lines. There'll be nothing going through the nothing connects to actually any of the sense side of it, so it won't actually do anything. So in this case, one of them will be used for monitoring the 24 volts, and the other one will be used for monitoring the either the 3.3 volts or the 5 volts. I think it'll be 3.3 volts coming out of the driving this board. Basically, it'll be monitoring this board's power, so it'll just this separately, and that will be connected to the ESP32, which will then be able to report power consumption. And as part of that, I can have safety stuff built in so that if somehow it detects high current that's like exceeding the specified power limit coming out of the lines, it can actually dim or turn off the lights because there's clearly a fault state going on there. But yeah, I'll be able to keep an eye on all of the power limits and all of that, which will be quite nice. So yeah, so that's what I ended up putting in this this board. Layout's a little bit ugly, but whatever. But yeah, so this is what I was faffing about with last night. So it all just fits nicely. That's the layout view. And the these tracers, they actually run on the top and the bottom, and then there's a via here just the top for to run to the current sense resistors. And obviously these tracers here to the chip only need to be tiny because they're just sensing the voltage difference. There's no current flowing through them. It's the current that's flowing through these that's tricky. So now that I realise that it's a 50 millivolt target, the voltage difference. So the voltage difference between here and here for the shunt should be 50 millivolts. I need to change which resistors I want to use, and what I did is I actually it's kind of small. Is there a? Did that zoom? This does not zoom. How do I zoom? Oh, here we go. Like, there we go. So you should be able to read that. So this is something I put together a while back. How did I calculate the current capacity of those tracers? So there's a calculator online, and the way it generally works is you're just working out what the resistance of the DC resistance of the tracers is, based on the copper thickness and the width, which gets you effectively a cross-sectional area, which tells you what the resistance of the trace will be over a particular length, which then tells you that your power dissipation will be I2R, which tells you what your voltage drop will be over that. So as long as that's okay, and then the power is effectively you can the calculators will figure out what the temperature increase over ambient will be. And I put it all through that calculator, and it comes out fine. Like, I think it gets kind of toasty if you run it at continuous 20 amps, but to hit that 20 amp limit, well, for a start, I don't think you actually can hit that 20 amp limit in the design that I've got. I don't think you can actually hit that. Like, I think I've overspec'd the supply by about 1.5. Maybe like 1.4 times. But to get anywhere near it, you'd have to run every single LED RGBW channels to 255 on every LED on every strip, which is just like, that's ridiculous. It's just, I have no reason to ever do that. I don't need retina searing blindness. Yeah, exactly, as long as I'm not reaching the TG. Which on this particular PCB will be actually slightly higher than normal. I think it's actually 150. I believe. I can't remember. I think it might be 150 because I'm using... so JLC do a free upgrade to an impedance-controlled stack. And if you're using a signal power... ground signal power stack up, so you've got 4 layers, and you've got signals and a power pour on the top, signals and a power pour on the bottom, and then grounds in the middle. The impedance control stack up just gets rid of the fiberglass core and replaces it with copper, so that the two inner planes are electrically connected. So you can't route anything on the inner planes, but I'm not, and I don't want to, because I want it to be a solid ground plane, which means that you effectively get 3 layers, but the middle layer is like a really thick, chunky middle layer, which means you get loads of isolation between the top and bottom in terms of like EMI issues. Yeah. It's like 130 or 140 is normal, but when you go for the impedance control stack up, I believe it bumps you to 150. The other benefit is that when you go to the 4-layer impedance control stack up, they actually reduce their minimum trace size and like minimum gap between pads and a bunch of other stuff. So they actually give you a more precise PCB just because you went for the free upgrade to the impedance controlled stack up, which for me, because I can't remember the last time I made a board that needed signals on 2 or 3, like signals on layers 2 or 3. Like, that's great, it's free, and I get better performance out of it. So yeah, here's this shunt voltage range. So I'm going to write this down because otherwise I'm going to forget. So max 81.92 millivolts. Recommended 50 millivolts. And that's, I believe, in either direction. It's not plus minus. Sorry, it's plus minus. So it's plus 81 millivolts or minus 81 millivolts, but they recommend 50 millivolts. So if I change that to 50, that changes a bunch of my calculations. So what this does is it takes a bunch of stuff from, in fact, I think the INA 226 has some different numbers as well now I think about it. Does it? Oh no, that's fine. So yeah, it's the same. So yeah, it basically takes all the numbers from the, although I think the measurement bits is slightly different. Now I think about it. That's not what I'm looking for. This. How many bits is this? Am I blind? Wait, what? There we go. Hello? It's confusing. $16 bits. Okay, so the native resolution is 16 bits. So this actually changes to 16 bits. And then let's say 20. So what I actually want is an ideal shunt resistance of 0.0025. Which they don't have an exact resistor for that. Oh, and then what this does is this here is I can put in a particular shunt resistance, and then this tells me what the actual results will be, and that's based on 2 parallel resistors. I don't have to do it that way. I can just set one of these to like 1 million, and then the other one to the actual value, or just double the value in both, and then it will come out on here, and that will then tell me the results. So there is a really useful little, or it would be more useful if I could do it do it in a different way. So I think if I want that, I think if I go for like 0.05, I think it is. Yeah, so I can use a 0.005 ohm. Oh wow, that's a lot of watts. Yeah, so I can use a pair of 0.005, which gets me to that. So there's no error. I don't know why that thinks there's an absolute error. Because that's the same numbers? Oh, because that's based on the cal register. Okay. So the cal register basically is what you set in the configuration via I2C of the INA whatever, INA 226 in this case. And what this does is, oh, this is actually INA 226 calculations. That's why then. I was thinking that this is far too convenient that it's correct. And what this does is this calculates what the cal register value needs to be, and this is based on the resistance and a bunch of other stuff. And then this tells me what the total absolute error, like this should be 6710.88 something, blah blah blah. So this rounds up to 6711, tells me what my absolute error value is in this, and then this tells me what my percentage error is, which is to within 2 decimal points, 0, which is fine. And I need 1 watt of resistor power, and it turns out here I can get these in 2 watts in 2512 size, which I think is what I'm using already. But actually what I want to do is if I can get them in a slightly smaller package that's still got good current capability. That's not in stock. It's not in stock. Oh, that's a capacitor. I enjoy that there's a manufacturer on here just called SUP. So there we go. Yeah. So when you put these 2 resistors in parallel, they load share. So the current flowing through them will split evenly due to KCL. And that means that you can have half the resistor power total that you need. And then because I operate on a margin of 200%, what I'm going to do is I'm going to use a pair of 1206 packaged resistors at 0.005 ohms, and they're going to be 1 watts each. So each of them can take the full power here. And then there's some design over provisioning in the design of the resistors anyway, so they can actually take slightly more than the 1 watt rated. So yeah, so the pair of these will do just fine. So I'll need to swap this one out for a different one, and then I'll need to change this later. But I'll do that off stream because I can't bother to go through and do a bunch of part entry for the moment. It's not a problem. So yeah, what will happen is both of these will be able to sense the current on this side. So yeah, so that will be useful. And as you can see, I've done a little bit of routing since we last were on. So this mess in the middle is basically the swap over stuff. So what happens here? And it looks more complicated than it is, but if you just follow the tracers, you basically got this channel 2 just comes down and goes over here, and you got this channel 3 that comes up here and goes over here. And you might also notice that the chips are slightly differently spaced on this, and it's because in order to get the horizontal width that I wanted to keep this down to 3.5 inches by 3.5 inches, preferably. So instead I've got this 3 inches by, and I think it's 3.6, including the overhang of the network connector, the RJ45 connector, which is fine. That's absolutely fine. So what's happening here is these chips, instead of being because this took up a bunch of space, they would have had to start like here. Instead I just shifted them back and then put these basically just routes back and then across, and then we got these in just groups of 4. So the last thing to put in here is these resistor and capacitor footprints, and these are, so on the left these are populated, I believe. Yeah, on the left they're populated, but if you take a look on here and then look at this, you can see that... okay. Oh, that's why, because I haven't got the variant. So in this variant, the all of these are DNP on the driver side. So yeah, on the driver side, the footprints are there, but there's no parts. These are not populated. I want the footprints there because I want to be able to reuse this board potentially for doing something else. And also, I might find out that I do actually want to have some of these on there, but I don't think I will. But yeah, so these are effectively just the these are the termination resistors. So you got these traces coming over and then just terminating here. Now, what I might end up doing is making these traces fatter, coming down to here, because there is actually a potential for some amount of current flowing through here. Not a lot, but some. And these are very thin traces. They need to be thin on this side because I can't route them. Oh yeah, actually I can't, because the whole reason for them being thin is because I need to get these two between between these slots here. I literally just can't fit thicker traces, like 1 mil larger, and they won't fit. Like these I could make bigger. These I just can't. I suppose I could neck them down, like they could come in and then neck down and then fatten up again, meaning that there's less resistance on this side. Like it would just be this area, but I'll have to look at that later. So yeah, so that's how all of this sort of, this is going to get swapped because I don't want power being input on a header. I will probably swap this out for a 200 mil, so 5.08 millimeter pitch terminal block that's going to sit here. But the tricky thing is that ideally I'd have it here facing outwards and then I'd wire stuff in, but this is the receive side, and if we take a look at the diagram, which I think is on this one, yeah, we take a look at this diagram, the transmit side is here and the receive side is here. So if I put a it would actually be here. If I put a terminal block here, it's pretty buttered up against the top of this cabinet, which I don't really like the idea of. And I know we're already we're putting a terminal here and a terminal here. This one faces down, not up. Although it actually doesn't matter. You could wire them any direction you like, really, because they're not getting assembled at the factory because the JLC don't do through-hole assembly. So these will be soldered on after the fact. So I suppose I could actually just put this on and then just flip the connector down and for this particular board and just have it coming down. I might do that actually. The other thing is that the terminal blocks that I'm looking at, they're not the kind that have the lip that overhangs the board and just catches on the edge of the board. They can actually be mounted in the middle of the board. They've got flat underside to them. So yeah, that would be quite nice. I might do that. So yeah, so this is getting replaced. So this will probably get like flipped round because there'll be a terminal block here, and then I would like this, so the fuse and all of this path to basically just come straight after the terminal block. And the height of these components, as you can see here, is they're really flat. I think the tallest component on there is the Zener, the clamping Zener. So yeah, it doesn't really matter if I have the terminal block facing inwards for one of the boards, for the one in the control box. That won't matter. So the wires can run this way and they'll clear this just fine. There'll be no risk of catching on this. I can always move it back slightly so I give myself a bit more wiggle room. So yeah, so that's going to get rejigged slightly. But yeah, so let's start some work on putting this together. So out 1, it's R21 and 41. Although actually, yeah, that's one thing that's slightly different here is on the input side, there's no pull-up resistors. On the output side, there are. And I made them smaller package resistors. I think these are 0805. Yeah, they are 0805. I'm possibly should have gone with 0603 for these just for the space, but we'll have to see how that goes. I don't have an exclamation mark project, unfortunately, YMAX, but this is show you the topology. It's an RGBW LED strip driver for an outdoor gazebo. So we basically got 24 volt power supply driving, getting converted into 5 volts for an ESP32. These nodes turn RGBW, so it's SK6812, very similar to WS2812 LED data into RS485, which is differential pair, so it's got some noise immunity and blah blah blah. This then travels outside, and then we've got 4 nodes, each of which turn data back into LED data with a 24 volt to 5 volt buck converter in each node to drive all of these. So that's what I'm working on. So yeah, let's see about. So the first thing I'm going to do is actually start putting in. It's 25, 26, 33, 34. 25, 26. And I believe it's actually at the bottom because it is. And then 33, 34? Or 34, 35? That's not what I want. 33, 34. I was right the first time. I screwed myself there because I was thinking to remember it, I'll remember the model numbers of the Nissan Skyline, R33, R34, and then realised, wait, there's also an R35, so I can't remember which one it was supposed to be. So this is out 1P. So this is basically doing the same thing as what happens here. And in fact, I think this actually needs to be flipped the other way because they're going to come up and round. And what was the clearance that I used here? I think it was just... yeah, it's just... 1. Yeah, okay, that's fine. It's basically... that? Was that right? Looks right. Yeah, that's right. And then the gap here was like, yeah, you basically just offset it ever so slightly, which is cool. I think it's like that. Which then... And just to remind you of the reason why I have 2 resistors on each side here. I need overall 120 ohm across here. Now, technically I should have chosen 120 ohm resistors here, but the 118 is fine. I did that while not really thinking what I was doing, but I've already got all the parts in and everything, so I can't bother to redo it. So basically this comes out at 2 resistors in parallel. This comes out at 56 ohms. This comes out at also 56? No, 56 would be 112. 57. 57, 57. Basically overall it comes out at... Wait, no, that doesn't make any sense. 59. 59, 59. So it comes out at effectively 60 ohms, 60 ohms, and then when you add them together you get 120. And I've split them because these are quarter watt parts, and I couldn't get resistors at this value that were higher wattage, and I need the sufficient power because the driver is essentially shunting current through these resistors, and they need sufficient power to be able to dissipate that. Hence the 2 resistors. And the way I did it on here was, yeah, basically just move this down here. And then this does the same. Yep. And then this will do the same on this side. So basically, oh wait, no, that's not correct. I don't know why I did that. That wasn't very smart. It should just literally be what's like here and then. Yeah, that's basically it. And then what I did, sorry, not like that. And then what I did with this last time, which I'm going to do again here, is just bump these slightly. Like I think these were 10 mil, yeah. Just because that way you get a bit better, bit lower resistance across those. And then in the middle, yeah, we have these traces that come out into the cap. Which cap is this? C14. Okay. Oh yeah, I forgot to move the caps up here. I'll move this back down so I can actually see where they are most of the time. Getting now though on the PCB placement. I'm hoping by the end of today this will actually be at least the this PCB layout stuff will be completed. And then the last work to do is, I just realized I've got these measurements on here and I don't remember what they were for. Oh, it was the gap between the chip and the back of the IC here, because I wanted to, back of the connector here, because I wanted to make sure I got enough space. So I knew that if I had space here, I would probably have space here. I know I do need some additional space for the additional resistors here, but I hope that'll be fine. Hopefully. What I am slightly worried about is whether this is going to bump into the resistors at the bottom here, and the same might happen at the top, but I'm not sure. Yeah. So then, yeah, this goes down to ground. So just copy our ground via. I can't remember why on this side. Oh, I see. Yes. So I put a stitching via here just because we've got this signal coming along. And I think this is a ground port anyway at the top, but I just like to have that there. It also just reminds me to not route anything too closely to this, because I don't want aggressors coming within too close a distance of the of this particular line. So this is ground, and I think I was making these 20 mil. Was I? How wide is that? 15. Okay, that's fine. I mean, they could be 15, they could be 20, it doesn't really matter, but I think 15's fine. So then this comes down, yeah. This is very weird music. I think I said this last time when this track played. I was thinking in the shower earlier that I might put up a poll on whether people prefer with or without the background music. Because, like, as somebody who watches streams, I sometimes don't like, just a bunch of silence in the background. But then equally, sometimes I I don't like the background music that the person's put on, and then I would rather just play my own background music over it if I felt that it was like too much silence in the background. So I don't know. Depends on what people prefer, I guess. Yeah, I won't read that yet, actually. So, and here comes the bit that's like kind of tricky. So R21 and R41 need to go top and bottom of these. 41. So like maybe they could go there, but then in the middle they're not going to fit. Like that's not going to fit because that's going to hit here. So it kind of needs to go below. But then to get the silkscreen in, like to get these numbers in, it's going to be pretty tricky. Like for R26, like I can move this over here and I can do the same thing on this side. Like R34 can come over here. In fact, R34 can go like that. Like that's not a problem. In fact, it can even go here. Like that's fine. The tricky part is that I suppose that's not too bad actually. Yeah, it just gets kind of tricky. Like, this is one of those things where if I didn't have to put these, didn't need to put silkscreen like identifiers down for all of the parts, it would be a lot easier. But since this is getting assembled at the factory, like I don't necessarily need them, but I want them because I know that like I'm going to be debugging and going, where the hell is R blah blah blah, or C blah blah blah, yeah, okay, I can find it on the board and then like find it on here and then find it on the board, but it's much nicer to have confirmation that I definitely got the right one, not that I've got like, you know, the board's upside down, I'm looking at the wrong side or whatever. So then, might actually want this the other way round because then, oh, I hate that. There we go. Blobs. Let's pants back on. Yeah, I might want to flip this round because that way I can have the wire on the left here. And it won't potentially go out that far. So this can just come down into here. And then, yeah, then I can have a VCC via here. I also discovered an interesting thing in Altium that is... jumper parts are a pain in the ass if you want normally closed. So normally closed jumpers, like oh, this was something I meant to talk about. Is you might have noticed these NC jumpers here. They're like this J2, J3, J4, J5, and they've got this like bit of copper in the middle. Using the jumper component type in Altium to do that breaks it. Like, it can't understand the concept that you've got two pins on the same net. If you try to connect, like if you put one down, it will decide that one of the pins doesn't have a net associated with it, and then if you set the net, it thinks there's a duplicated net, and it can't figure it out. So instead, if you change the component type to net tie, it now understands that that's just the same net on both pads going through. It's really weird because the thing is, like, you could just make it as a normal component, but then you get collision errors because you've got this piece of copper going between the two pads. It's very weird. But yeah, if you set it as a net tie, it just works. And the reason for these jumpers is that you'll notice that the input side, the outputs from the input side, so the single-ended outputs, go into this connector, which is usually how we receive data. It turns into WS2812 or SK6812 signals, and then this goes back into these ICs and then is sent out again as RS485. On the control box side, we're not using the receivers. We're directly driving signals into this pin header. So this is basically how the data gets into the system. And I don't want that data going back to the driver sides on these chips because these are supposed to be outputs. So you don't want to drive them with a voltage and they can mess things up. So for the control board, if you look carefully on here, you can see that the solder mask is pulled back over this trace. So all I need to do is just basically go in with a knife and just cut these on the board. So it's just convenient that they're normally closed and I don't have to go through and just put a little solder blob on them. Although for the SHT35 boards that I sent out the first batch of, the SHT35 breakouts have a similar thing, but it's normally open. So these are NO pads on the other one, so it's just basically two pads with nothing connected. And I was worried about how difficult it was going to be to solder over the two pads. On my reference board, on the one that I been using for a bunch of the testing, I needed that to be in the alternative address anyway. So it's an address selector jumper. It can either have address 0x44 or 0x45. It defaults to 44. I literally touched them with the soldering iron with a bit of solder on, and it flowed immediately on. I didn't need any extra flux or anything. It just flowed straight on. So I know these work wonderfully. So if I need to reconnect them, they do a perfect job. I'm happy with that. Yeah. And if you're wondering what it looks like when you get one of those boards, I've been making these, which is it's got a bunch of conformity information on. I think the autofocus will just about find. Yeah. So, it helps if I put it in full screen. There it is. There you go. So you get a bunch of these graphs and stuff. This is unique to your board when you get it, and all of the QA stuff that goes on it as well, which is fun. Oh, that was lucky. I thought I just caught the stop recording button, and I remembered to record this time. I forgot last time, and I had to use the Twitch export thing, which was annoying. But yeah. And if you want one of those, there it is. Oops. If you want one of those, you can buy them from there. Yeah, so it was quite nice. Right. So yeah, I'm happy that those jumpers work nicely. So I think this is fine as a layout. I might... That doesn't really change anything, does it? Like in this particular case? No, I think I like it like that more. Although... Oh yeah, no, I moved that there for like that because I couldn't get that to go. See, one thing I worry about is like when you got this big nest, it's like which resistor is which. But I think it's quite clear here because this is obviously R45 because it's the closest part. This only has this designator here, which means that it's not for this. This must be for this, this must be for this, and this must be for this. So it's like, it's fairly clear. And again, this is just for, if I get these and there's a fault, or, I need to go do a bunch of debugging and testing and making sure that things are sane, then I need to, I would only use these for that. Like generally I could just turn off all the designators and have a much tighter board, because the pick and place machine doesn't need, you know, it doesn't read any of this. Nobody reads any of this during the manufacturing. It all just goes into an automatic pick and place machine, and blah, 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 blah. There you go, all your parts are on, and job done. But yeah. So this then goes to ground, which actually, the cool thing about this is that on this top layer, I don't think I need a wire here. Like, for anything where I'm decoupling, I'm putting wires because I care about that. In this particular case, I actually don't care, because the top layer ground pour will actually connect directly to this pin with thermal relief. So it won't just, like, you know, solid flow over, because then you wouldn't be able to solder onto it easily. Have thermal relief. But I don't need a wire here, because this is just a pull up. Pull down. That's a pull up. That's a pull down. So I actually don't need a wire here, which saves me some space. But I'm conscious of how close we're getting here, because if you look, you see how little space we've got here? And that's about as close as I want to get. And this is going to get more complicated here, because I've got to squash all of this that's here into here, and I'm already using this lower. Yeah, it gets a little tight, which is why I was wondering whether I need to go to 0603 on these, because I might need to go to 0603. The other thing I can do, which is really ugly, is rotate these outer resistors. Because if these will fit in horizontally, it gives me more space to work with in the vertical. Because I could have this resistor effectively here, and then, you know, let's just see what that would look like if I did that. Like, sanity check, will this fit? Oh, that's so tight. I'm not sure I like that. Because if the tolerances on this are wrong, yeah, I know. But if the tolerances of this are wrong, they'll catch. I know the symmetry because it's so nice, but if I've got to get this whole circuit, this whole piece here, and you see it's hanging over here and hanging over here. I've got to get this here. Yeah, okay, I've got some wiggle room here, but this is going to mess up these. Like, I could move these slightly higher, I guess. Have less of a gap in this middle. Move these down, move these up. Maybe. We'll see how it goes. It's just because I've basically got to get this again, plus this resistor a second time in here. Which is... Oh, that's going to be a tight fit. I'm not sure that's going to work. Let's see. I mean, I'm going to move this silk screen anyway, because I can totally move this label, like this designator here, which then gives me some space here. But I don't know what I'm going to do with the next one, particularly here, because this is going to bonk into everything. R33 and R25 silk screen. Where to? Like, I guess I could do something like this, but I really hate doing that. And the thing is, it's not so much about moving these closer anyway. Although, if I did do it this way, well, if I did do it this way, what I could potentially do because this is So this could then go... And then the next one would go here. Maybe. Like, let's see how that works. So what's the next set of resistors? Is 27, 28, 35, 36. I think also actually, if I move this over, these can actually step ever so slightly closer. I think that's okay. So then these are going to have to come out this way. So then, yeah. So then this would look like this. This is where the layout starts getting like really, really tight. See, the thing is, these are all do not populate anyway. So the main thing I'm worried about is just this shorting onto one of the contacts. But I would like to be able to put the parts in if I need to. So what was the pull up? R22. Well, that's a pull down technically, but that's on this side, right? Yes. So then this would go like this. Yeah. Which obviously puts the silk for the next run would put the silk screen under it. But I think actually if I were to move this down, it then gets a bit weird because it's like, how does R41 R22 like fit in here without looking weird? Like, I think that's okay in terms of distance. Like, it's only 30 mil, which is not a lot. Like, it's less than a millimeter. So between this pad and the back of this, it's like a millimeter. Yeah, it's 1.143 millimeters. Yeah. And that's 1.13 millimeters at normal value. Like, not like there could be tolerances that shift this like back and forth. It's pretty tight. Now the thing is, I don't necessarily have to do it like that. I could move this up and just do it like I did before, like this way. Like, is that less? Is that even actually less? There's literally a 5 mil difference. 5. Like in this case, I'm going to do it this way because I've got the space here. I'd much rather leave space here to do it differently if I have to. Because here I can just do what I like. Like, I've got the horizontal space to, you know, just make this work. So then I just need a VCC via here. So this would then go, so this would come down to here. That's grounded through because the ground pour will cover these and this, so that's fine. That goes to here. This goes to here. So that's fine. Seems mostly reasonable. Thing is, I can actually shift these one further back if I wanted to, but these aren't the problem. Like, it's getting these other ones in that's tricky. So then it's R35 and R36. So these would be like this. And so actually, if I'm going to follow the way that I've been doing it with the rest of it, this would go here, and this would go here. Ha! There's not enough clearance. It actually has to go like, yeah, it has to go like that. Oh, which is actually how the other one was anyway. So okay, that's fine. I kind of like that. I can see that working. So now obviously I need to route both of these down here. Wait, what? Oh yeah, duh. So you know, that is actually fine. What? Why you no connect? Oh, because I'm a moron and I've got these upside down. That's possibly going to work okay, maybe. Why you do this? Seriously? There we go. Symmetry. It's funny, I keep getting these net antenna warnings. The DRC basically tells you whether you've got a net that forms an antenna. But they'll go away once I actually hook this up, because at the moment basically what you've got is you've got this driver driving an output that's just a wire, which just doesn't go to anything. So it is an antenna. That's what it is. I'm just going to be back in 1 second. I'm just going to go get a drink. So I will be a minute at most. See you in a second. Sorry about that. So then we need the capacitor, which is 15. Oh, that's annoying. So what I can do here is basically just move these labels down, move these designators down, and then, oops. Although, I will actually move that one up because I don't want... that feels like it's really close and doesn't need to be. Like, that was just silly. So yeah, so this goes here, and then we can just move this cap down. Because we just can. This can be here, yes. It would be nice not to have to deal with all of these, but oh well. It's like commenting your code. I don't think this is actually supposed to be 15. I think it's supposed to be... Wait, that is 15. So what's going on here? Why is that? Oh, these are actually too close together. They should actually be like one further apart, I think. Yeah, looking at it, that is the case. That's why. What's funny is this playlist that I've got on. It's a bunch of YouTube videos of, like, you know, the no copyright sounds, blah blah blah. You know, for use by Twitch streamers and all of this. And I came back after uploading one of my videos to find out that 2 of the tracks were copyrighted. It's just like, you had one job, you call it this, and it's not. God's sake. Which is fine, because it's the type of copyrighted where they basically just stick ads on your video and then yeah, they stick ads on your video and then pay the money back to the music creator. But like when you specifically do it to not have that, it's just yeah, it's very irritating. And the thing is, like, it doesn't really affect me because I don't really monetize any of my YouTube stuff. Like, I think I have like I think I have the monetization set up, but I'm not monetizing any of the videos because the amount that I would get from them is basically nothing for the annoyance of. And to be honest, I would expect that every single one of my viewers that isn't watching on an app would be using an ad block anyway that blocks YouTube ads, so I wouldn't get revenue from that anyway, and like that's fine, I do it. Like why would I expect anybody else to do any different? Like, ads are annoying, and mid-roll ads on stuff like this I hate. Like, it's so annoying. The ones that bother me the most are the ones where they've put mid-roll ads on it's like something like with really soothing content, and then they stick some horrendous like mid-roll ad on it, and you're just like, you're ruining my experience here. This is very irritating. Yeah, exactly. It's just, I don't care. That's why I don't want and the reason I don't want the copyright notices on them is because they can ramp up the number of mid-roll ads. Because I think by default they're like running now. By the default, I think they're running at least one on every video, which is just awful. It's just horrendous. I would much rather just say no, I don't want the money from it. You can bugger off. Hell, I'll pay you not to roll mid-roll ads. But yeah, I think once you get the copyright strikes, it goes up to like 4 on one video, which is just crap. Is that supposed to be a ground wire? That's supposed to be a ground wire. Yeah. Rant. Almost went into Airwolf again. Repeat of last stream. Me singing Airwolf. What a theme tune. So I like how on because these are marked DNP, it's not showing 3D models. It's just showing the pads. That's cool. I hadn't noticed that it does that before. Because like this part is the same as this part. These are the same. But because these are DNP, they just don't show the 3D models. Smart. I'll have a bit of this because I haven't eaten much today. A sandwich earlier. I nearly just tried to eat cardboard. Right. So we need the pull down on the top, which is R22. No, R22's here. Why is R22 going to... Oh, sorry, no. R42. It's kind of blind there. Even though I don't have to, I am going to have this resistor sit on this side because I would prefer not to have that clearance. Oh, speaking of doing this, I've been so tempted to buy... If the website will work. I've been so tempted to buy these. Because, like, I haven't... these work on the FX888D, which is what I have upstairs. Like, so useful for taking off passives. But, like, that there is the price of the iron. Well, not anymore, it's gone up a bit, but when I bought it, this is exFAT as well. But yeah, that's the price of the iron. And that's just the iron. Like, that's just this. That's just the handles. Like, if you want a stand to put it in, as low as £43 for that. I'm being good for now. I've not bought it. But if I find myself needing to do any passive rework on these, might have to get those. Because the thing is, they're not that useful for placing parts. Because, like, you can just solder passives down dead easy anyway, one side at a time. Like, trying to do both at the same time actually feels like it would be maybe more tricky. Maybe. Guess it depends. I guess if you tinned the pads and then switched over to the and then placed it on a pair of tin pads and then heated both at the same time, it would flow quite nicely. But like, I'm a bit unsure on that workflow. But definitely for taking passives off of boards, those are fantastic. Like trying to do it one side at a time. And then of course, even if you did have two soldering irons, you've only got two hands. So then like trying to put them down and then lift the part off. No, I'd much rather have something like that if I was going to do that. But I don't know. And again, I just realized with this one, if I hate that it does that. Turn that off. I just realized with this one that if I flip this around, hello, if I flip this around, then I mean, it would work either way because there's ground plane everywhere, but this nice big pad just gives you a nice space for this to connect to. Yeah, sod it. I'll just go here. Oh, that's not supposed to happen. Yeah, so there we go. So that works. So then what's going to happen is these are going to come up here. I might, in fact I will, I'm going to move this over here because I would rather have this, because we're going to have those tiny 3.5mm traces coming up here, and I don't want it to have to duck around this VCC here. I'd rather it have just free space to come over. It'll look nicer anyway that way. So yeah, I think this proves that this is going to work because in terms of layout, because this is just going to get mirrored on the top, right? I think this is fine. Like, worst case, if this overhangs too much and I'm concerned, I can just stick Captain Tape over this. Like, it's not being populated. I can just stick Captain Tape over the whole thing. I think that's fine. Because, yeah. Because, again, these aren't being... These ports aren't being populated at manufacturing time. These are being shipped with everything else soldered but the through hole. So I can Captain Tape this down, put this down, and then solder it in if I'm worried. I'll check the fit when they arrive. Yeah, okay. So, this is R42. So the next one is going to be... keep doing that. You know what, I'm going to close these two because I keep clicking the wrong things. Now I only have save all. So 2930, 3738. And then we've got the last two, 2343. And I believe C16. Not to be confused with C16. So, here's the thing. So now I'm thinking about it. I think this original layout would have worked fine, because what we got a reasonable gap. This does keep the gap a bit better though, I guess. Yeah, I guess it keeps the gap slightly larger between the edge of this and the nearest part, so whatever. So what I'm actually going to do, now I think about it, is I'm going to start on this top one, because the referencing of the positions of all of this is actually relative to this, and it's easier to just put these down in the normal position and then do the rest. Oh, right, yeah. For a moment, I was confused and... Wait, is YouTube doing this thing again? I think it is. I have autoplay on, but I'm playing a playlist, and it's not doing a thing. We just listen to this one. There we go. Yeah, YouTube's being weird. So, yeah. So the inner sides of this are supposed to... It's about that much space, wasn't it? Yes. And this is backwards. So these are actually supposed to go on top. Cool. So then this comes over here. And this here. Well, that's weird. Why are they... There we go. I was thinking one of these looks like it wasn't on the grid properly. So then, again, this goes like that. This like that. Sweet. So then C17 needs to be over here. And then we got this R44, which is the pull down, and it's the pull up. I'm gonna do this on the bottom. Oh, I just sort of... What did I do with this? Oh, I see. Yeah, this is where I did this thing where I had like the... Wait, what? Ah, yeah. A very weird drum kit for this track. It's very like Yeah, this is very like default drum sound. Like you can't see it at the moment. There's a drum kit over there, and this kit sounds like what that sounds like when you turn it on the first time. Getting kind of Rammstein vibes from the that sort of male choir noise in the background. Oh. I forget which Rammstein track it is that this is reminding me of. It's one where it mentions a church in the first line, Kirche. Aratanish. Yeah. It's an early track, I think, if I remember correctly. That's like the first album? 1997. So yeah, pretty early. So what's going on here? Okay, so the way I did it here was just... I am not confident enough in my German that I would attempt to sing along to Rammstein on a live stream. Also helps that I haven't heard that track in ages, so I can't remember a lot of the lyrics. Now, if it was Zonna, that I could sing along to. That is a tune. Sie ist der hellsten Stellen von allen. In terms of music videos, I think that's got to be like top 3. That's a particularly good one. Deutschland obviously taking the top slot because, I mean, obviously. Oh, this is on the wrong side. I was thinking like that looks weird. Yeah, that is not the correct one. Should be the resistor for the next. Yeah, so this can go here. Over slightly. And then I do want a wire on this side because see, I don't care about them on yeah, I don't care so much about them on the pull-ups and pull-downs. Because there's basically no current flowing through these. These are just literally just to set the voltage. You're talking, you know, nanoamps going through that. Okay. It's nothing. Very weird snappy drums in this. Like, I think they were trying to go for drum and bass drums, but this sounds more like metal drums. Like, those bass kicks are very, yeah, metal drum kit. Okay, so yeah, so then these come in. So the first thing I need to get on there is whichever of these goes up to, so I think the top one goes to ground, right? So I think it's R43. So yeah, this goes on the negative side to ground. So this would go here. And then this goes here. I messed that up before, but I think that's correct now. So you see what I mean about this setting the position of where these sit, like further back up. So rather than trying to work out, oh, what's the offset of here, just do them from the top and then come down. And I think this then goes. No, that's on the bottom side because that's the P side. So that's P, that's N and N. Here we go. So that and that. I wish the like click and drag thing wasn't so stuttery. Like, that's slow and weird that is. So this would go here. Did I just literally stack these right up against each other? Yeah, I did. Cool. That works. The thing about the these green outlines on the parts, they're not actually they're not really part of the normal, like, they are part of the normal footprint because they've been generated, but they're basically just like guide marks. You can actually go over them. I could move this to like here and that would be also fine. But it's just a nice guide mark to keep things reasonably spaced. And I just don't like colliding them that way. I think you do get a DRC fault if you do it, but as long as you just have to read what it actually says, because the DRC fault will say like component outline, or I forget what it's actually called, but it'll be like whatever collision between the outline of this part and the outline of this part. But if you then check the DRC for pad-to-pad clearance errors, as long as you don't have any of those, you're actually fine. You can squash them closer. They are just guidelines for the keeping things reasonably spaced out. Reasonably. I think actually these want to go up here. So then C16 comes in here. Oh, this is backwards. That's irritating. See, this wasn't quite so close on this side. I think the reason for that is that I'm not actually sure why that happened. Oh, because on this one I flipped it. Wait, no, that doesn't make any sense. What's going on here? Why does that have space, but this one doesn't? It just might not be quite centered. Because, like, there's more space here. Oops. Whoa. Do not want to do that. There we go. There's more space. Oh, for God's sake. Stop it. Yeah, there's more space in this gap here than there is here. Like, that's nothing. So I guess these are just not quite centered vertically. So what I kind of want to do is shift this up. I have to shift these out. Which is a little gross. I guess I can move them like here. I guess that's fine. And then I can move this cap up. This designator can go like over here. I don't care. Oh, maybe not over there, but somewhere there's more space. Go over here. That's fine. So then this can flip around here. And again, ground wire because it's on the cap. Although I'll just copy the VCC one, but they're the same. It's fine. Doesn't hold the net name anyway. Oh wait, yeah, no, wait. No, that is a resistor. So that is supposed to go to the VCC. My bad. Oh, it was supposed to be for that one. Ugh. Yeah. That was not what I was trying to do. I am going to move this designator back a little because what I noticed on one of the other boards, on the SK6812 boards, was that when I was doing this, parts of the silkscreen were getting cut off around where the holes are. So I just need a little better clearance. Like, it'll be obvious enough as to what they are, but I think that's fine. Whoa. What did I just do? Ah. I put it in planning mode for some reason. It's supposed to be 15, I believe. Wait, is that 15? No, that's 10. Cool. Oh, and yeah, no, that's wrong anyway. So that's supposed to be 10. That's also supposed to be 10. And then that is not supposed to be like that. That's supposed to come down to here, and this is 15. Did I put these two close together? Maybe I did. That's supposed to be the gap? Yeah, that looks right. Cool. Yeah, I think that's reasonable. So then it's just R23. This is literally the last part. The final part. Cool. Yep, look, no more parts to place. It's not technically true because I've got this to like rejig and swap out for a different part, and I need to swap the current sense resistors, this one particularly. I think it's this one specifically, but both of them really. So, cool. Right, so now I need to route the, I'm trying to remember how this worked last time. I believe on this side it's the same deal. So it's, yeah, it is the same deal. So this comes out here, and this needs to be a 3.5mm. So this, actually what I'm going to do is I'm going to route the middle ones first, because they're going to be the trickier ones, and that's going to inform how I route the rest. Now, how did I do this on this one? Because I know that the middle ones needed to be flipped. So in 3P I think is fine. Or out 3P in this particular case. I think it's just directly routes. And then 3N is in like a weird location, because 2 is actually down here. So 2 needs to come up, round, and into here, which I think is what I did here. Yeah, look, 2 comes whoop, round. So in this particular case, what happens is, 2N comes up here, and then like that, and then this one. This is where it gets a little trickier, because the yeah, I'm like routing around a bunch of weird things. And it needs to come up here, back this way, because it needs to go up into, this is the point where they can join together, and then this goes into here. So yeah, you got this 2P, 2N, that's fine. Which then informs me in terms of routing 3N, because I now know that this also has to go on a slightly more circuitous route. Like, you would think I could just go around the back here, but then that messes up everything else. So I come down here, and then across to here, and then down into this. That's okay, and then So this top one. Wait, these are swapped as well? So what happened in this? Did I have two where I had to do that? Oh, I did. Okay. So this actually needs to come down because... oops. Yeah, this needs to route over here. So then this top one comes down and over there. Cool. So then this one from here has already been done. And this one's just trivial because they're on the right side. So this just comes up and straight in there. And then this is the same. So, if I then take the polygon pores that I've got, restore the shelled ones, and then repour all. So now if I run a DRC, okay, so we've got some DRC failures, but that's fine. Oh, yeah. Slight issue in that I forgot to actually connect these. And then... that it? And polygon actions repour all. Like those are connected now. Oh. Really need to hotkey that. So there's still rat's nest here that's not connected. Oh, that's because this didn't connect to this. It's fine, and I think I want to make that. Oh. Oops. And that's 10 mil. And then this out 3N is also not connected. I believe that's fine. Let's DRC that. One last unrouted constraint. What is this one plus here? Oh, I just forgot to connect these together. Whoa, that is 100 mil trace. It's about 10 times more than I wanted. Oh yeah, I forgot this goes around the back, doesn't it? Yeah. So then, yeah, repour. Is that the only? That might have been the only disconnected. Okay, I have one clearance constraint failure. Oh, because the neck here is too small. Just, I think with these, it just makes more sense just to route from the trace itself out. Like these little curves on the edge here are problematic because you get these like weird, the etchant or whatever they use can't get into those tiny little holes, and they can cause problems. So it's better to just do things that way. So let's repour all again. Do a DRC. Cool. So, do have some DRC failures. What? Minimum solder mask silver constraint 8mm between pad and free, whatever free is. Have I got some weird copper sat around here? I don't know what that's about. I've got a lot of these. So okay, so these are fine because so this is 8mm solder mask to solder mask clearance, so that you won't actually get solder mask between these. That's not ideal for it's not ideal, but it's allowed. It's basically just because the footprint doesn't allow for sufficient clearance between the pins. So these are all fine. So anything that's related to this part is fine. I don't care about that. There's one minimum solder mask clearance here, and it's saying that something here is like not far enough away. I can't tell what's going on there. What is this? Oh, I see. So this pad here is actually just too close to this via. So I think the easiest solution is just to move the via back ever so slightly, like that much. Which I think is fine just to do that and then repour. And then let's DRC this again. Yep, that went away. So finally what we've got is we've got silk to solder mask clearance. That's just here where we've intersected the silk screen of this. Ideally I wouldn't do that. In this case I don't think I care, because when this goes to manufacturing they're just going to cut that piece out, and that's fine because it's just a square. Like, who gives a shit? Again, okay, that one I can fix. Let's turn off regions and polygons. Don't want to snap onto those. Like, I think that's fine now. So that one I fixed. And this one. Object not found. So that doesn't even exist anymore. So let's... and again, this is silk to solder mask. So let's repour all again, just as a final... Tools... DLC. I think this is okay because so I've got silk to solder mask clearance here. So yeah, just those three, and it's literally just U9 and U10, which is these two. that are failing DRC for the silk screen gap between the pads, which is fine. Which means this is, like, I could, technically speaking... That's a noise. Okay, then. Yeah, so technically I could just send this to production. Which is cool. I won't, because I want to fix this yet. So, let's hit save all. Yeah. Cool. And there's only one thing on the back, which is this VCCR jumper. So, this looks cool. So this bottom layer is the power port. So this is all VCC, aside from this trace, which is VCCR, which is VCC for the receivers. That's the only thing that is. So that when I'm not using the receivers, I can just cut this, and it means there's no power going to any of the receivers. So because the inputs are in a floating state, I don't want them doing weird things. So I can just cut this on the this one, yeah. So on this node here, I cut this, cut that, solder into here. Jobs are good. I was looking at, I was considering maybe having a different connector than this, but I think given the space that I've got, just a header is the only real option that I have. Like, there's no real alternative. One thing I am going to do is I'm going to do some silkscreen stuff on here. Like, I want to move this over because there's space, and that way I can easily label this, you know, channel 1, channel 2, channel 3, channel 4. Because just looking at the board, like, have I got it the right way around? What's what? Particularly in, like, you know, come back to this in a few years, I'm not going to remember any of this. So that's what I'm trying to do. Place a string. That's a ground. That's not very useful. So there we go. So we get this CH1. There we go. And then that looks reasonable. And of course I can just for completeness, I hate that I have to have this slightly higher because of this damn spot. Like, can I move this down? Oh, has to go there. Yeah, I hate that it gets bumped. It's fine. It's just minorly ugly. It's worth it though to have that TVS that close. Like, having a very short path to the TVS over here means that this will take any of the any shocks from this. Just sort that straight out. Cool. It's kind of cool. I like it. So we've got a nice little bit of space up here if we ever need to add anything more. I could probably put some silkscreen info like up on this side. So in the controller, this right side here, I was about to point at my screen and then realized that obviously that, why, no, you can't see that. This side here is facing downwards. So this is the top, this is the left, and this was with the right. So the INA226 INA226 power monitors are on here. I still need to fix this resistor. This is wrong, and this is wrong, so I need to swap these out, which means probably rejigging a little bit of this, yeah, so then we'll have those. So I need to put some silkscreen on that as well, because I will not remember what they do in however many. That'll do. Oh, that's large. Let's move that off. So that's the 20 amp side. And then on this side, let's move this area. And then I think this was supposed to be, I think the target for this was 4 amps. Cool. So, so what I need to do is, so I've got these calculations. So let's say maximum expected current is 20 amps. See, the thing is, yeah, the resistor voltage drop then becomes 50 millivolts. Now, if I change that to, yeah, so it can get to like 32 amps before it hits the actual limit, whereas 20 amps is what the voltage drop should be. So at 32 amps, I would hope that something would say, no. And one thing I do actually have that I didn't show on this schematic here is that one of these DIN little clips here actually has a it's a fuse holder, and inside that there's a I think it is a 20 amp fuse that goes in that. So the power from the yeah, the power from the supply goes up into the 20 amp fuse, which then goes up into the power monitor side of this, which then comes back down and then distributes out to everywhere else it needs to go. That's the plan, at least. So, yeah. That's about right for that. So, yeah, I needed to recalculate what was going on here. 20 amps. So it was a pair of 0.005. And I think I'm going to go with this 1206 part from SUP. What's the difference here? Those are quite large. It's not enough power. Large again. Oh, that might be better actually. Oh, that's a 5% part. I'd much rather a 1% part. So yeah, I'm going for this one. So, let's go into the schematic. Actually, no, let's go into the schematic library. Any part? Oh, that's the schematic document. Libraries. So, in the library, we're going to have... do I have a 1206 already? Is 1206 right? Yeah, I have a 1206 already. Duplicate this one because this one's going to be the closest. Oops. Yeah. So this is a swap the MPN out, and it's made by SUP. Such a funny name. So let's go with that part, supply part number in, and repeat that here. This is a 1 watt part, 1%, 0.005. Yeah, I put that in there. 1206. What's the point? Sorry, I know you can't see this. I'm just looking at the data sheet for this resistor. It's weird, because yeah, this one doesn't really manufacturer doesn't really list like maximum current. It's weird that the other one did. I think it's just because it's convenient, but it should just be 1 watt. What was the value? Should be 005. This is 1206, which is correct. I think the girls with their nails done. Yeah. So I'm going to get rid of some of these attributes because they don't apply to this part. Rid of that one and that one. Maximum working voltage, I believe. Yeah, it's root PR, which just whatever really. I guess they just don't specify. So I'll get rid of the working voltage because they just literally aren't specifying what that is. Yeah, I think the power dissipation is rated at 70 degrees. believe that's what it's rated at. Yeah. Standard anyway. Yes, it is standard rated maximum. So that's fine. Operating temperature range is... What? It's not correct. It's obviously not right. I think they typoed something here because they've just said that this resistor only works in 25 to 125 degrees C, and I'm pretty sure it'll still work at 20. I think it's supposed to be minus 25. Yeah, minus 55 to 170 degrees. So I am correct that that was wrong. Not 1,170. No. It's a nice furnace resistor. So yeah, this is getting yoked and replaced with a pair of resistors, which is... I'll make sure I got that right. Where's the... This one. Yeah, 0.0025. So this is 0005. So components. And this is the one with all the brackets and weird stuff in the name, or at least one of them. This one. So yeah, so we get... it's the best noise. Cannot wait for the next season of this. I know it's the last one, but Stranger Things is so good. Mystical. Also reminds me a bit of like this interpretation of it reminds me a little bit of the music from Interstellar. Oh, I love the audio on that movie just in general. And I would really love to hear the Interstellar soundtrack played on a giant you know those huge pipe organs, the ones that like fill a building, the monstrously large ones. They've got such a like a resonance and timbre to them, yeah, it's such a good tone, and I would love to hear that played on that. It's just such a good sound. So I actually didn't decide what I was doing on this second one, so I know the resistor value is going to be wrong, but so if we're targeting let's say 4 amps on this left one, so on 0125. That's funny. Okay. That's fine though, because 0.025? 0.025? That would be spot on. So let's find out what the because it's not 0.0025. Well, what was making me laugh was it's basically if you if the resistors were a decade value higher, you could have just had 4 on one side and 2 on the other, which is ugly, but wow, you can get very small resistors. That kind of power. I don't want to charge that much. 40 pence. 19 pence. For a 1206 at 1/4 watt. I would need 2. but that's still only 10, which is less than the total cost. So if it fits on the board, yeah, I guess. How big is the part that's on there now? This one. Yeah, that's a 1206. This would also be a 1206. So there'd be two 1206s there. So I would actually have to I'd have to relay out this side. Unless I can find a 1206 with a higher power rating than 1/4 watt, which I feel like shouldn't be that difficult. Like, that seems a third of a watt. It's not much better. That's a much larger package. Much larger package. I was hoping for a 1206 that has like a half watt rating. Don't think I'm going to get that. Or a 1210, because a 1210 would be fine. That'd fit. That's cheap, and that's a 1206. And it's a third of a watt, which I think is fine. Wait, what was the... Oh, I do need two anyway. I do need two anyway, because it's... Do they do 0.0125? No, they don't. Of course they don't. That'd be weird. So, okay, so I do need two anyway. I could get them in 0805 1/4 watt, but they've got a minimum order of 50 of them, which is fine. I mean, it's not a minimum order. They basically just charge you for 50, even if you only use... 3, but it ends up being more expensive that way. Whereas I found this 1206 part, which is a third of a watt a piece. There was another one here that's cheaper and a 1/4 watt. What was my power budget on this? It's what, 200 milliwatts, so be over double. So I could just use the cheaper 1/4 watt parts. Wait, is that cheaper? No. It's cheaper to use the third watt parts. What? Oh, it's a 5% tolerance. That's why. Versus a 1% tolerance. So yeah, I'll go for the 1% tolerance ones because the tolerance on this tolerance on this matters. So yeah, let's import some new parts. Schematic library. So this is one of the Uniroyal 1206s. So I can just clone an existing 1206. In fact, I'll clone this one because it's very similar. It's the same series, I think. This is 0.025 ohms, 1% 1/4 watt, 1206 ROHS, and the part number is that, and the resistance is 0.025. It is 1/4 watt, and then the LCSC part number is this. One thing I will need to do off stream is the tedious job of going through and making sure that all of the components that I've put in the BOM match expected values in the LCSC part number, because the LCSC part number is what they use to actually pick the parts. They don't look at anything else. So if I've accidentally put something wrong in the LCSC part number field, they may pick a different value, a different part, which is particularly bad because every time I add a new chip resistor, I clone an existing one from the same series, so it'd be very easy for me to accidentally get the wrong part number in there and end up putting, like a 118 ohm resistor or a 0.025 ohm resistor where I need a 0.004 ohm resistor or something like that, and just completely throwing everything off. which would not be ideal. So yeah, this is a 1206. Now, that's one thing I will check with this. What's the working current maximum on these on the 1206? Because they do list it. Yeah. It says the rated current of the jumper is 2 amps, but the maximum rated current is 10 amps, which is probably just means that it starts heating up beyond that point, which is not ideal, but yeah, I guess who cares? Should probably be fine. I'm slightly concerned by that on the, because the other resistors that I'm using, if I remember correctly, the ones I just made, these. Oh, these are the ones from SUP that just don't rate the maximum current, so I think that's fine. Because the PD over the diode over the resistor is already here. There's half of this per, so that's fine. So that can go away. And then we'll replace that with the new component that I just created, which is up here somewhere. .025. That really bothers me when people mix like this and they duck the lead so hard for the kick that you get that sort of feel. I don't like that. Going too hard with the compressor. Do not like. Okay, so these will, the last ones of these are 44. Yes, this would be 45 and 46. Oops. $47, $48, and $49 and $50. There we go. We've got 50 resistors on this thing. So, what I'm going to do is, because I know these, so for a start, I'm going to shelve all the polygons so I can work on this a little easier. There we go. And then I'm going to delete that. I'm going to delete that because they're not going to be in the... And then I'm going to update the PCB. So then it gives me these. So... I think these are on... No, these are on this side. Noise. Such a weird noise. Oops, no. So then this goes like here, all the way. And then these designators have just used the default size. Let's change them down to what I usually use. So then this mega chonker. Wait, this is backwards as well. What the? Such a weird synth. So if I move this across, oh, that's odd. Not routing straight, but it's fine. What I might do on the top layer, actually, now I think about it, just replace this whole thing with a polygon. Same on the bottom. Well, but same on the bottom side, not on the bottom layer. Although, no, I won't do that, because what tends to happen when you do that is, I'm also going to change this to like 100 mil. So what tends to happen when you do that is the thermal relief you get on the between a polygon and a pad. So in order to be able to solder through something, you're adding heat to a thing, and if that thing can take the heat away quicker than you can put the heat in, it doesn't heat up. You just warm the whole board up. You don't heat the point up. So what they do is they put in thermal relief, which is like these little crisscross connections instead of connecting directly to it. The problem is that for high current carry, the thermal relief basically just adds a bunch of resistance that I don't want. So yeah, in this case, I'm not going to do that. Why are you being a dick? There we go. So yeah, let's change that to 100. We can have some proper chunky traces coming off of this. Yeah, you can see what's happened here in this. It's just gone weird. What is this? Seriously, what is this? There we go. In fact, you know what? I'm going to redo this. Oops. I'm going to redo this because there's no reason not to move these sense resistors up and out of the way, because like, yeah, there's no reason not to have them higher up. Go there. Which would mean that I can have the wires basically like here, and then the current sense resistors, turn component selection on. The current sense resistors can sit like nice and like in such a way that I can make easy connections to the one here and then one here, either side of the wire. Yeah, so then this comes into here, and then this like very nicely comes out and Whoops. Oh, dear. Oh, I kind of want to leave that in. Okay. Did not consider how that was going to look. Oh, the best thing is that on the bottom of the board, when I repeat these traces, it's going to look exactly the same and it's going to be really visible. That's awesome. Swear I'm 12. Really, YouTube? Again? I've also lost where the hell my I accidentally put some other thing on my... Yes, I did. That's why I can't see it. Is the stream alright? Because... YouTube just decided it didn't want to play the next video. I wasn't sure whether my net had just dropped or something. Not getting any... Yeah, not getting any drop packets or anything. Yeah, just YouTube got to the end of the video and just was buffering and I was like, oh no, what's going on here? So all of these DLC failures. Oh, it's because of the, yeah. Right. Wait, what? It's not what I'm meant to do. Oh right, yeah, of course. It won't look like that on the back because it's literally just there to there on the back. Yeah. That's what I was looking for. Top there. That's really funny to me. Nice. That's very funny to me. Right. God, how much shite is here? Just go away. Cool. So, aux tracks, pads, wires, texts. Cool. So then let's get rid of these because these are going to get messed up when I move this back. Wait. What is that? That's... Okay. Wait, no, that's wrong. So the mirror from blah 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 is 0.005. That's correct. And these... Oh no, that is right. Sorry, misread the number of zeros. I was like, hey, why is that a lower value? But that's 0.025 and that's 0.005. So yeah, that is correct. And again, these designators are wrong in terms of size. 35 rather. 35mm, 8mm stroke. This can actually come down here. I think it is for this one. Yes, it is. Although actually I wanted these higher, didn't I? Yeah, because I wanted these to go basically in the middle here. Ooh, Tron sounds. Yeah, like that. That's fine. And then this can go here. Although, yeah, no. I swear I've heard that sound. That da 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 da. Like with those bells, I'm sure I've heard that sound in a demo. What? Why is that? Why is that still like throwing an error? I think that should be fine, and then that's fine. Oh wow, that's even funnier. And then bottom layer. Goes. It's the same deal. So yeah, get one of these trace width calculators. So in this case, it's 20 amps, 1 ounce thickness. Let's go with a 30-degree rise over. And what's the total distance here? This is so it's about 600 mil. Maybe, yeah, no, it's an inch, 1 inch, let's say. Yeah, so this is where it gets a little tricky because Yeah. I think these traces are going to get kind of warm. Because the flow through here at 20 amps is something like it's quite high. At 20 amps, like it's gonna get warm. So really, it should be something a bit more reasonable. Really, it should be like 320-ish mil trace width total, which over 2 layers brings it down to about 160 width, and these are 100. Problem is, that's kind of silly. Like, that's just... And then the wires just don't make any sense to me. I need multiple wires, I guess. Yeah, I guess I'm gonna have to do this with, like... It just doesn't make any sense to me, because you've got this pin here that, like... I guess it's connecting to all of the board. So, like... Yeah. So I think on the... I'm going to have to, like, change this up a little. And then on the bottom side, not on the top side. On the bottom side, I'm going to have a... I'm going to duplicate these wires, which unfortunately does ruin the joke a little, but... This needs to move, because I can't go there. Hello? There we go. That's too close together. I know that. That's fine. So on the top side, that's not the top side. On the top side, there you go. Like, oops. Yeah. What's going on here? Like, why is that thrown a failure? There should not be a... Like, what? Oh, I guess if it's like, no, there is no gap there. I think when I do a full DLC, that's going to fix itself. But yeah, so, if I can. No, that's annoying. But yeah, so we got all of that over there. And then on the bottom side, what's going to happen is we're going to have just big polygon pores over all of this. So this is basically just going to be from like here over to here. And then down to here. Like, I think that's a reasonable-ish way of going with this. Regions. No, polygons. And that should be on S1. And it should pour over the same net objects. So if I re-pour that. Yeah, so that's cool. And this is what I was on about with the thermal. The thing is, I can't modify this, I don't think. I can't modify the thickness of the... Is that in part of the design rules, actually? It might be in design rules that I can modify it. Connect style, here we go. So the conductor width is only 10 mil, so I can change that. So let's change that to 20. Globally. And then it's... Did that fix it? I don't think I fixed it. So it's got a 20mm expansion. Like, oh, that's what's happening here. Oh, right. Okay. Wait, no, that doesn't make any sense. See, it makes sense here. Look on the wires. You see how they get these nice big chunky. It's just the green that's like the keep out here. So it's actually the black is the part that's connecting. So that's nice and thick now on all of these, which is fine on the wires. But I'm confused by this because polygon connect size. This is it. This is what I was trying to think about. So yeah, the conductor width, you want this more. I want this like probably 40mm or something. Like, what happens if that's 40mm? And then I re-pour this. Yeah, look, that's much chunkier. Although with them being that close together, that actually messes it up slightly. So let's re-pour again. Nope. This needs actually to be quite a bit further back. There we go. So we get this nice big connection between the two. Just go like that and see what happens if I do that, because I don't want it too far apart. No. It does want to be that far apart. There we go. And then this plane actually can be like all the way out to here. There we go. Why is that showing on top of the parts? That's weird. That's really weird. Like, what? What happened there? That's really weird, isn't it? Like, what's going on there? Huh. Not sure what's going on there. Like, why is that? Very weird. Like, what happens if I... Yeah, it seems to be like texturing the I don't know why that's happening. Yeah, it's very weird. I think that's a bug. I think that's a bug in Altium because, like, oh, what? That's weird. Okay. That's really odd. Have I, like, put some weird mode on that's done this? I think I might have put some weird mode on that's done this, actually, because that seems not right. Huh. Yeah, that shouldn't look like that, should it? Like, what? Have I... Yeah, I don't know what's I don't really know what's going on there, but that's fine. In fact, I think it's actually better to do this. Oh, let's just... Oops. Nope. Let's not select polygons. Yeah, I don't really understand what happened here. You know what? Why do these have designators? Like, why do all of these have designators? They should not have designators. Yeah, and this seems to cause some sort of like weird DRC fault when I... And then when I do connect them, it doesn't. Which is very strange. But oh well. So this goes up to here, and then this goes over to here, and then this goes over to here. Like, you can't have them all connected for some reason. It messes everything up. That's fine though. Yeah, I don't know why this is like... I'm gonna just quickly Google that. Oh. Yeah, weird. I don't really know what's happening there, but whatever. So let's get rid of all of this. Suppose I could just... Yeah, I might just put these as planes on the top, you know. No, because then... Yeah, no, I think I'm just going to leave it like that. It's too close. And then, yeah, let's do the same thing on the top here. Except these are supposed to... There we go. That's fine. And then on the bottom side, we can have another plane. Put a little corner on that one because I want to keep it away from this other trace. Like, I don't want anything... I know this is on the top layer. In fact, yeah, it wouldn't make any difference really, but yeah. Yeah, it's weird that it's drawing this like this. I don't really get it. It's very odd. But yeah, this is supposed to also be connected to... Why can't I... Oh yeah, polygons. So this is on S1 plus. So let's re-pour the power of those. Ah, you see, this is what I don't like. Yeah, this big gap. So I think this is fixed if you do this. No, it isn't. I guess it doesn't matter too much because you've got these fairly thick traces going in. Like, this is fine. Like, what's happened here? Like, what is this? Is this on the top layer? No. So why the hell is it here? Like, let's shelve it and bring it back. Design. Restore 4. Polygon actions repour modified. Oh yeah, you see that looks fine. But what's going on the bottom? Because now that polygon's missing. Like what? What's happening there? I shelved it and it disappeared. So wait, hang on. Let's take this bottom one, shelve it. Take this top one, shelve it. Oh yeah, it's still here. Just didn't get re-poured for some reason. And now it's fixed. So yeah, that was a bug. That was a bug. And I think on the top layer, I'm going to make these traces bigger. There's also a bit of trace in here, but I'm going to actually have to change that to just pick tracks. There we go. Yeah, I'm going to change these to like, I don't know, like, well, that's too big, 150? I know there's a constraint on that, but I'm going to change that in a minute. That's okay. I'm going to change my design rules because I basically just set a max just because you have to. Yeah, I just set it to 100, so I'm just going to change that to like 200. I think that's fine. There we go. So that's much better. So we've got these big chunky bits of copper coming through. And I think that's okay. I think. Because where was the calculator origin? Here it is. So at 20 amps for 1 inch, I need approximately to get a, let's say, change this to get a 30-degree rise in temperature, centigrade, above ambient, I need a 300 and, let's say 390 mil trace in total effectively. That's 170. That bottom one's a lot more. I think it might go, like at 20 amps, I think it might go a little above that. Like, I think we're more likely to get like a 50-degree rise maybe. Like 45 to 50-degree rise above ambient, which is pretty hot. But that's only when you're absolutely slamming because 20 amps is a ton. So, and the thing is, because it's squared, it's a sort of, you get this ramp effect where if I bring that down to just let's say I'm okay with a 40-degree rise above, that's 325 mil at 20 amps. If I bring that down to just 15 amps, the difference goes from 325 mil equivalent trace width needed down to 220. So you lose a third off of your trace size requirements for just dropping 1/4 of the power. Like, that's only 5 amps off. So, and then a much more reasonable 10 amps, I would only need, in fact, yeah, I'd only need 100 mil trace for that. And in fact, with the amount that I've got there, which is like what, 100 and 200 on 300 odd mil. Yeah, like, that's not going to rise above 10 degrees above ambient. Like, that's going to go up by 10 degrees above ambient. Which is not a lot. At 10 amps. So I think that's okay. I think that's okay. I might chunk these up a little. Like 120. Did I make this one 120? No, I made this one 100. Yeah, I think that's okay. Although I'm going to change this one to like 185. There we go. That way you got coverage all the way around. Yeah, I like that. That's better, because then we got tons of current carry capability here. And then this can come up here and just go straight into this, and then this can come down. This actually also goes into here. Then we run. Wait, what? Oh, right, yeah. Why are they flipped? How was this routed before? What was going on here? Also, yeah, what's happened to this SDA line here? Oh, I see. I get it. The SDA line comes down here. And then that goes to there. Yeah, and then, although this needs to come down like that, and then, yeah, okay, that's fine. I was very confused there. And I don't know why that's complaining, because... Oh, because I've just tried to... Because I'm a moron, and I'm trying to connect the wrong things. Oh, I don't like how close together those tracers get there. Like, that's really tight. There we go. You know what? Oop. Yeah, no. There we go. I think that's okay. Like, not ideal rate running around the like routing around this, but I think it's okay. Which means that this doesn't need to go, like, this doesn't need to be weirdly routed up here either. Like, have that much. That's cleaner. And then I can take this down a little, so it's a little further away from this. I know it's there, but that's fine. And although actually, no, I will move this back slightly because what I want to happen is I want the yeah, no, that's too close. But I want the ground pour to come in here, because I've got ground pin here, and I've got ground pin over here, and I've got ground pin here, and I obviously the ground pin over here won't reach for this, but this all around here becomes then one nice little connected section, so that this, any return currents can couple into this plane. So that's fine. So I think that's okay. This one, yeah, like 5 amps at most, and at, let's say, 30 over ambient, I only need a 50mm trace here, and this is 100. So these are, this side is fine. The 4 amp to fight, I mean, I've got 4 amp here, but yeah, I think I designed it around 5 amp. So I might actually change that slightly. Yeah. So this side is okay. It doesn't need any more, you know, ridiculous stuff going on. The wires here are fine. Like, you can, there's a, I think there's a, yeah, so there's a, these are doubled up. So yeah, we're absolutely fine here. This is the only one where it gets a little sketchier, but the I think that's fine. It'll get warm at 20 amps if you're really hammering it, but we're not generally really hammering it that hard anyway. Oh wow, I've been streaming for 4 hours. I should probably drop off before too long. Yeah, I might call it a night because it's 2 AM. So yeah. I will finish off this last bit, this top section here, this top left section, off stream. And then, yeah, get that all tidied up. I might add some test points. You can see I've got one here, this VCC test point. I might add a couple more elsewhere on here where it makes sense. Like, it doesn't really make much sense for these, like, you know, CH3, 4, 5, whatever, because we've got pins for them. But maybe something over here. I don't want to do them on the differential signals because I'm worried about them basically acting as like little patch antennas. Yeah, I don't know. We'll have to see. But yeah, I'm quite happy that we've now effectively got the board done, barring, you know, a little bit of work over here. Yeah, I mean, it'll look nicer when I do this. Like, let's restore all the polygons and then re-pour them all. There we go. And now that's what it's actually going to look like. So we've got all the pores on. And if I flip it over, there we go. So that's what it'll look like on the bottom. I think that's reasonable. Yeah, so the only section we don't have a power pour on the bottom is here, which is fine because this is where the signals just swap over, so you don't need any referencing around there anyway, so that's fine. This is just the VCC for all of the chips on the receiver side, which obviously I can cut. Yeah, and then on the top side we got ground continuity everywhere, it looks like, because if I didn't, Let's turn this on. No, that one on. There we go. Yeah, I've got this. I know you wouldn't be able to read it very well in 1080p because it scales badly, but remove dead copper is selected, which is why we've got this like dead section here where there's no ground. And in fact, actually, I think I want to move this like up and then move this down and then re-pour this top. There we go, that's better. Just get rid of that little dead section of copper. So the only dead sections we've got are around the backs of here, which is fine because these are decoupled to ground anyway. This net is just basically going through a cap to ground. And there's plenty of ground referencing around it. So this section here is fine. This section here is also fine. Same deal for all of these. We've got the same on this side. That's all fine. This can't do anything about. And I want these kept separately anyway. So whatever. And keep in mind that the middle two layers are ground planes. So, and they're completely uninterrupted. Like if you look at these, like there's nothing in the middle apart from where we've got wires going through. So that's all fine. It would be nice if the ground came in here, but we've got a ground pin here, so I think that's okay. Yeah, I think that's okay, because we've got the ground around here, so this is just going to couple over this side. This is the only thing that's sort of left a bit without a reference, but that's only a very low current line anyway, and it's only a few millivolts, so I think that's okay. I'd be more worried about and it's also only near to S2 plus, which is this anyway, so they're so close in voltage that I don't think it matters because it's just a DC offset between the two, so I think that's okay. If this was like SDA, then I'd be more worried because you wouldn't want SDA coupling into these and you get noise in your readings. And if there was any high frequency currents on this, you wouldn't want the noise on this. This is still very funny to me. So I think this is all okay. It's probably one of the most packed boards I've ever made. Like, that's pretty packed. It's cool though. Yeah. And there's enough clearance around these. Like, this is a little on the tight side, but there's enough clearance around these that you can get a screw in. And I'd be using, they are metal screws, but they've got like a black lacquer or something on them. So I think it's okay. I don't think that's going to hit there. I could move this up. I should move this up actually. So let's just shelve polygon actions, shelve all. Yeah, I'm going to move this part because it is a little on the close side. And I've got space to do it. Like, there's nothing just stopping me. Yeah. There we go. Just gave myself ever slightly more clearance there because. So these are 3 point. Yeah, 3.3 millimeters. So they're for M3. The M3 screws that go in here. Now, if I go onto one of the mechanical layers and place a full circle, let's just do that and believe. Wait, what? Ah, yes. I believe that the heads on M3 screws are usually about 5 to 6 millimeters. So the radius should be, let's say, 3 millimeters. So that's fine. And in fact, it may well have bumped before where it was. So that's fine. I think that just fits nicely. And then I'll use this guide again, just here. Yeah, like it gets a little close to this pin. Like that's kind of a little close. So I might just get rid of those and then just get rid of that. Get rid of that. Why are all these selected? What have I not got selected? Wires, that's why. Let's turn that off. So, yeah, this would go just ever so slightly further over this way, and then let's get rid of that and that. It's always useful to give sanity checks on this. And what I am going to do is that now I know that that sits that far out, I'm going to move these a little further because while it's unlikely that I damage this trace, I never want to, you know what I mean? Like you get this mechanical scratching of the solder mask and the silk screen from putting screws in and stuff. And these are only going into, these screws are only going into the soft, yeah, it's going into that plastic of the, sorry. It's going into the plastic of the mounts that then go onto the DIN rail, which means that these don't need to be tightened really hard. Like they can just be tightened fairly loosely. And what I might do is get some foam, little foam washers, little foam M3 washers that I can put on these, although foam brings potentially SD issues, but yeah, I think that's okay. I mean, the top side I don't even need to care about because everything's so far away. There's basically nothing in the top side of this board. I could probably have shaved a bunch off the top of this board, but I don't want to. I think this is fine at 3 inches. Yeah, plastic washer would work as well. Yeah, you can get little nylon washers. I might use that. The reason I was thinking foam is because you can get a good mounting force on it, and it doesn't matter how tight you try and push it. With the plastic washers, what can happen is if you over tighten them, they can snap. Whereas with like a padded one, it like puts some force on. But to be honest, it doesn't need massive mechanical strength. It's going inside of an enclosure. It's not going to be, you know, tugged around and bonked around. Yeah, I think it's fine. So there we go. We're doing a little sanity check on the parts of it. Tools, pulling and pause, restore, and then repull them all. Cool. And oops. Cool. And I'll do one final DRC, and then I will call it an evening. Ha! I moved this silk screen, I didn't think. Yeah. There we go. It's fine. Cool. That's kind of awesome. I like it. I'll do one last thing before I go. What? Oh, yeah, because I'm in the wrong layer. I was trying to place copper text, which you can do. Well, you know... What is going on? Hello? What just happened? There we go. Something very weird going on there. I don't know what's happening there. Like, I couldn't... Oh, Altium has actually just crashed. That's fine. Luckily, when that happens, because of how Altium works, no, it's fine. Everything was saved. When you run a... when you run a task, like run a command in Altium, which includes things like trying to place something on text, it kind of like separates it out into its own thread with its own... it basically kind of launches it as its own little task, and then if it fails, it's actually fairly good at not messing everything up. It can get into a weird state, but no, that's fine. I have already saved, so all good. So yeah, instead of trying to carry on doing this, because clearly something went very wrong there and broke, just looking now, yeah, there's a solder mass clearance there, but that's fine because we want as much there as possible. And in fact, what might end up happening when I put this together is I might end up actually putting solder over these wires, because I would like these to be preferably filled, but they don't do filled wires. So instead what will happen is excuse me. Yeah, instead what will happen is I'll just solder directly over the tops of these. But yeah, I think that's it. Cool. So unfortunately couldn't do the little text thing that I was going to update there, but that's fine. Yeah, so I'm going to call it a night. Thank you for hanging out and chatting and everything, and see you soon with more random fun things, more electronics. Still going to be working on the power monitor stuff, 16 channel mains power monitor. Got some design changes to make on that based on some recent discoveries. So all right, cool, take it easy and have a good evening.